Hello, students. I don't know about you, but I think that math class needs a makeover.
I think I need a makeover. I don't really know what that means because I don't really know what a makeover is, but I'm going to pretend that that's something I need.
It's when you like put a mask on.
That's all I get is just a mask.
Yep.
So I can just like take a piece of paper and put it on my face.
That's such an improvement.
I see.
All
All
right.
right. So we're going to dilate and translate. So dilate means multiply, get things bigger. Translate means move. Cubic and quartic stuff.
I like it.
Even and odd stuff, more. Power functions. And then possible graphs. Okay. And we're supposed
Cool.
to describe the graph of the equation y equals x to the n, where n is an even integer.
Ooh, this sounds like what we were doing when we couldn't even.
That's true. So for the first part, I think for the most part, we talked about the graphs would look like this. They could flip over, I guess, but they looked like this for an even integer.
Interestingly, they couldn't flip over based on this discussion or based on this example.
Right.
Yeah.
I'm talking about future students. We could flip those over, but right now that's all we know. Basically, they both go up. So as x goes to positive or negative infinity, the y stuff goes to infinity.
Cool. So looking at the second part, which is odd integers, instead of both going up, we have graphs that were on the positive side, it goes up, and on the negative side, it goes down to the left. All right, so now, applying some foundation. I bet that's a makeover term.
So that's like you put the stuff on.
Yeah,
I know.
see, you put a mask on that, you your foundation.
There we go. So we got x squared. We have 3 points of x squared. Symmetry of the basic quadratic function to graph 2 other points. Okay, so if they have 1, negative 1, 1, 1, that means I have negative 1, 1, and negative 2, 4. So that's showing f of negative x is f of x, because when I plugged in a negative, f of negative 1, that was the same as f of 1. And f of negative 2 is the same as f of 2. That's the symmetry about the y-axis.
And we know that's because if we plug in a positive number or a negative number to that thing squared, you get the same results as an output.
Yes.
Cool. Okay, then we're doing the same thing, it looks like, for the cubic function, but now we have to kind of graph this ourselves. So if we're trying to find cube values, 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. And 2 times 2 times 2 is 8. So those points, 0, and then 1, 1, and then 2, 8.
Use the property of symmetry to determine 2 points other than the key points. I don't really know what the property of symmetry is, but I think that's where they're talking about the symmetry about that point. So if we had 1, 1, we had negative 1, negative. Is the property of symmetry a thing that I just don't know?
I don't think it's a capital P property of symmetry. I think it's that this is a property of this function. It has symmetry.
Got it.
And then connecting those, we look something like this.
Then use these points to graph the basic. Okay, so we did that.
I like it.
And that's f of x is negative f of negative x. So f of negative 2 is negative f of negative negative 2. I made that as confusing as possible for them.
Surely did.
But the negative negative 2 is f of 2. And then negative f of 2 is negative 8.
Cool. I'm going to jump to the next page away from that monstrosity.
Holy words. All right. Linear, quadratic, cubic functions are examples of polynomial. Polynomial function can be written as something x to the n. Sometimes you write that as like an x to the n, and then an minus 1, x to the n minus 1, etc. So basically those gray squares are coefficients.
So this could be like something x to the 4th, and then something x if 4 minus 1 is 3, and then something x 4 minus 2 would be 2. So it's just kind of showing that we have decreasing powers kind of organized in that fashion.
And you don't have to have every term. Like one of those somethings could be 0, so we
Sure.
wouldn't have a cubic term, something like that.
I like it.
And then we got,
This would be called a quartic function.
yeah, that's what they say. And a quintic is a 5th degree. And then we got these transformations. We have an A, B, C, and D. And it says A and D affect the output values. Those are Y values.
Hmm.
And then B and C affect the input values. Those are the X values.
So
And they
this,
tell us what they all do.
so there's this stuff that is the inside of this function, and anything on the inside affects the x. I think we talked about that a little bit
Mm-hmm.
in previous videos. And if we're multiplying that function by a, or we're adding d to that function, we're affecting the function value. In other words, the y value itself, the output.
And if you relate this to vertex form of quadratics,
Mm.
if that's an easy thing for you to think about, I don't know if it is. If you had something like this, the 3x minus 3 would be the x movement. That would be moving us right 3. And then the plus 5 would be the y movement up 5. So you can see that we did get into that a little bit with quadratics.
Okay, and there are a lot of words in this table and talking about all the things that are happening here. Um, are there any of these that uh, you think are more important or less important for students to feel pretty comfortable with?
I think the least important part is the b.
I'd agree with that.
For the functions that we're talking about, until we get to something called, well, you guys know what trigonometry is, but there are sine and cosine functions. You can't really see this that obviously. And so I think B for right now is the least important.
The other thing that I don't love about this table is that it makes it seem like there are like a billion different things that are happening, when realistically, these two are the same thing. It's just a matter of, we know that negative is one way, positive is another way. The same thing for these two are the same thing happening. We just know that positive is one way, negative is another way. And up here we have this idea that, well, if a is bigger than 1, it's different than if a is between 0 and 1, and that's also not true. It's a matter of really what you know from geometry dealing with dilations and whether something gets bigger or smaller based on multiplying things.
Yeah,
Um,
and for that one, they actually had 3 tiers where you have the bigger, smaller, and then you also have the reflection. And it's all the same thing. It impacts the y values. It might make the y values smaller and negative, something like
yep,
that. So it looks super scary, but it's not too scary once we start playing with it.
I agree. Okay, so there's going to be a matching activity that is going to be set up through Desmos, um, and that we're going to use this to play with.
And we might want to talk about the Sanjay idea. So explain why Sanjay's reasoning is not correct. Rewrite the transformation to identify the correct B and C values. So on the previous page, they wrote it like this. And you can see that Sanjay does not have it written that way. So Sanjay has 2x plus 5, but B is not necessarily 2, C is not necessarily 5. I mean, B is 2.
Yeah.
But you want to rewrite this as 2 and then x plus something.
Mm.
And if you factor that 2 out, that's going to be 5 halves. Because if you think of multiplying that 2 back in, distributing that 2 back in, that'll be 2x plus 5, which is how we started.
That makes sense.
And so the B value is 2, and the C value is 5 halves, or negative 5. I would say negative 5 halves, right? Based on how no, because they wrote it as, yeah, because how they wrote it. They wrote it as x
yeah,
minus c, so then c would be negative 5 halves.
yeah,
Which maybe makes it make more sense that that's a leftward movement for you if you think about
that
it
does
that way.
make sense. Cool.
But the other transformation stuff they will do. And this is a wrap up of that, so we're not going to talk about that either.
Okay, so this would be something that they should probably take a look at on their own, and then we'll talk about in class.
Yeah.
Ooh, so now we're going to build and sketch some transformations.
This function did come up in the so odd we can't even video. I remember showing that this was an odd function. So we'll do it again for part A here, but we've already done that. To show whether we're odd or even, we plug in negative x.
Mm.
And I think I maybe did this one in the other video. So I'm plugging negative x, and then negative x cubed is negative x cubed. Did I write the wrong thing?
Yep.
Oh, thank you. And then negative 2 times negative x is plus 2x. To show that that's an odd function, you just have to show that that's the exact opposite of what we started with. And what we started with was x cubed minus 2x. The exact opposite of each of those pieces is negative x cubed plus 2x. So that is an odd function.
So everything changed because it was so odd.
That is true.
All right. Then we have 2f of x for part B. And the goal is to use the reference point to figure out what's happening here. So this is going to be 2 times the y value for what we're looking at, because we know that f of x is the height of the function. So the corresponding point would be 0, and then 2 times 0. I'm going to actually write that out just so that we know that that's there. We've got 1, 2 times negative 1, and then 2, and then 2 times 4.
And I did the same thing down the bottom because they're asking the same question. H of x is 1/2 f of x. It's just instead of a 2, it's a 1/2. So I showed my work on the left there and then put the answers on the right.
So if we were to plug these in like it asks us to sketch a graph of this, yeah, we'd end up at, for the red one, 0, 0, 1, negative 2, and then 2, 4. Oh, I totally screwed that up. 2, 8. There we go.
It's okay. 2 times 4 is not 4.
And then the property of symmetry would, I like that I'm calling it now the property of symmetry. We can't really see where that negative 8 would be because it'd be way down here. But our graph would look something like this.
I'm gonna email them to fix these graphs. All right, and so same idea for the points I have. And so it'd be negative 2, negative 2. So it'd be like this. Kind of missed 0, 0, but you see that it shrinks it up vertically a little bit.
And it looks like the one that was times 2, it made it stretchier vertically.
Yeah.
Okay, so here we've got a different graph, and we've got to verify this is an odd function again. So I'm going to do the same thing. I'm going to plug in negative x. We've got negative x cubed plus 1/2 times negative x. That's going to be negative x cubed and minus 1/2 x. And that's the exact opposite of d of x. Therefore, this is an odd function. Cool. And then it looks like we're doing the same things that we did for the first two. I think this might be a good one for them to try on their own.
Yeah, but the numbers are inside, so that might be more confusing. They were on the outside before, now they're on the inside. So we have to think, okay, what does that impact? When they were on the outside, they impacted the y values. But now it's not going to impact the y values.
So we're trying to find, in other words, a value that would make the same input as 0 when we have 2x. So I could write like 2x is equal to 0. Therefore, when I divide by 2, I get x equals 0.
So I'll do the same thing. 1/2 x equals 0. So x equals 0.
And then for the next one in, we've got, again, we want an input of 1. So 2x is equal to 1. When I solve that, I get x is equal to 1/2. I was about to write 1/2 comes 0.
Yeah. So the y values here are not changing, just the x values.
Right. And then same thing for the third part. You've got 2x is equal to 2. So x is equal to 1.
Or 9. We got to plot these. So 4, 9, 2, 3 halves, 0, 0. And then since this is odd, we just do, like if I have 2 3 halves, I'll have -2, -3 halves. And again, we can't plot the other piece. So my graph looks like this.
I've got 0, 0. I've got 1/2 3/2, which is like here. That's going to give me -1/2, -3/2. And then we got 1, 9, and we can't see the other part. So mine is going to look something like this. And this is, aside from the scale of the graph, which makes it kind of narrow overall, we can see pretty clearly that when we multiplied the x by 2, it made the graph squishier this way. We multiplied the x by half, it made the graph squishier the opposite way. All right. Ooh,
Complete
we're
the
using some
table to
geometry
summarize the
language.
graphs. Ooh.
So there's a lot of mathy stuff that's going on here in terms of uh, this like what they put in here. Is there something that would be more important for our students to be able to use instead of this notation? Or is this reasonable notation for us to talk about? I don't know.
I think we'll be okay talking about it, and then we just need to clarify because they use stretch and compression, which are not words that the kiddos are necessarily going to use.
Hmm.
And so I think we'll be okay. We just need to make sure we're clear in what we're talking about. So that first row, it says vertical stretch dilation. So that means that was the first thing Mr. Carlson did when he multiplied by 2, where the graph went this way. So since 2 is bigger than 1, we stretched this way. Since we're dealing with x cubed, we have symmetry about 0, 0. And then the even, odd, or neither, it's odd. I'm a little confused because,
It's because of what's down at the bottom.
okay, so all of them will be odd until we get to the last 2.
Yep.
Because there's no, since we're the first 1, 2, 3, 4, 5, 6, the first 6 are, we're not moving the graph, we're just kind of stretching or shrinking or flipping it. We're going to keep the odd nature of things and we're going to keep the symmetry. That's not going to change.
And just to kind of explain why that changes when we get there. So vertical translation, if we move our graph up, suddenly these points are not matching on opposite sides of 0, 0. They're still have that type of symmetry, but where they are symmetric around has been moved. And we're not really going to talk about how to kind of reference that. They're just not odd functions anymore.
So to fill this in, when a is bigger than 1, that's going to be a vertical stretch. When I think I'm just going to say a is less than 1, that's going to be a vertical shrink.
That makes sense.
And
And then for the horizontal stuff, that's when we had kind of the opposite stuff going around. So I'm going to, for the first one, just say this is P of X is equal to C times B of X.
it's
That's
not
when,
c times b of, no, it is. No, it's c of b of x, right?
yeah, C of B of X. Does it
Okay.
C times?
Yeah, I was just,
Okay.
you confused me. Wanted to make sure, right? C of b of x, not a multiplication problem.
And for a stretch, that's when these went farther. We saw that was when B was less than 1. So when in Mr. Butterworth's function, the last one, when it was a half, that made the function stretch wider. And same thing for the other one. I'm just going to write B is greater than 1. Everything that we have with x's is kind of the opposite of what you'd expect it to be, which is kind of a good way to think about that.
It's also confusing because a horizontal stretch goes this way, looks the same as a vertical shrink.
Yeah. In fact, for the functions we're looking at is the same. It's just you'd have to manipulate things to make it look the same numerically.
Right. So when we get to sine and cosine, it will be more obvious with those. But with these ones, that's why before I was like, B is not that important because it gets a little weird.
Right.
So
I'm
how
just
do we
gonna
reflect across the x-axis?
remind us that this is a vertical flip. Because often when we see x-axis, we think horizontal.
Hmm.
Um,
That's taking y values and making them the opposite sign.
it is, and that should give us a hint of whether this is an A or a B thing. Because if we're taking y values, it's going to be the thing that affects y, which is the A stuff.
So that's
Um,
is that a is less than 0?
it is. And similarly, for reflection across the y-axis, this would be a horizontal flip. We're talking about changing x values to their opposite sign. So this is going to be if b is less than 0. Cool.
And then vertical translation, we've already seen that and we talked about that. That's the d value. So that's the p of x is c of x plus d. And the d moves you up or down. If d is positive, we move up. If d is negative, we move down. Because that movement, we do not, we're symmetric about 0d, I guess.
I would agree.
So symmetric, but 0d.
And
And
with that,
we are neither odd nor even, assuming d is not 0.
yep. And then for the horizontal stuff, so this is talking about if p of x is c of, great choice of letters, x
Yeah.
minus little c. Uh, and the reason we use this as minus is we talked about everything for x's is backwards. So if we're doing like x minus 2, what that means is moving right 2 units. If it were x plus 2, it would mean going left 2 units. And similarly, for the symmetry, this would be something that's like shifted here. This would be around the point c comma 0. And then we also end up with neither for odd, assuming that c is not 0.
And the question I always ask myself to figure out the horizontal translation is what makes x minus c equal to 0? Because that helps me remember, because it's counterintuitive that when you have x minus 2, we're moving to the right. But if you think of x minus 2, set that equal to 0, you get x equals 2. So that means we move 2 to the right.
I like it. All right, now we're doing the same stuff with even functions. And is this something that we want to do out again, or that we want our students to try on their own?
I think they can do this because there's not much difference.
Yeah, the one that I'm going to suggest is going to be different in terms of results might be this one, not different in terms of the transformation part, but in terms of the symmetry and odd even stuff. That might be a little bit different than odd functions.
That's true.
But everything else is going to be, I think, exactly the same-ish, except for the symmetry stuff.
Yeah, same
Cool.
idea.
All right, and now we've got to do more than one transformation simultaneously, which sounds like a lot of fun.
So what I would do to start is we're going from f of x to g of x. I would start with 0, 0. 0, 0 is the middle of my curve.
Mhm.
And I'm staring at this trying to figure out where things are going. And 0, 0 goes to 0, 4, negative 4. So 0, 0 goes to 0, negative 4. So what that means is we're going to take f of x and we're going to subtract 4. Perhaps.
Perhaps.
That might be one of our options. We also have to pay attention to the stretch nature of things, where we're going from 1, -1, sorry, 1, 1 to 1, -1. And then we're going from 2, 8 to 2, 20.
So would it be fair to say that, and we can really only do this well looking at the first point of this graph going from 0 to 1,
Mhm.
that here we're increasing by 1 and here we're increasing by 3. So it seems like this one is 3 times as big. I'm going to check again on this one. Here we're increasing by 7 and here we're increasing by 21. So that one looks 3 times as big as well.
So that's a y value movement. So does that mean that's an a value thing?
I think so, because we're talking about multiplying by how much bigger it is. So that sounds like a scale factor. That sounds like a dilation to me.
Got it.
So I'm going to say that for this, maybe a is equal to 3, since we're multiplying by 3. I'm also going to
And
say it's positive because this is still an up graph.
so does my -4 still work with us?
Let's take a look. So if we did this as x cubed, or sorry, 3x cubed, and then -4. So if I do that, is 1 times 3 is going to be 3 minus 4 is -1. Then we've got 3 times 2 cubed is 8. That's 24. And 24 minus 4 is 20. So that actually works perfectly without having to do anything else.
And it's interesting, you forced it to be x cubed, which it is, but you could have just said, I want to do 3 times the y value and then subtract 4 and not even worry about what the function is. So if I do 3 times 0 minus
Yeah,
4, -4. If I do 3 times 1 minus 4, I get -1. And if I could do 3 times 8 minus 4, then I get 20. So you don't have to care about what the function
that's fair.
is.
So then looking at this, we're saying that this is going to be 3 times that original function and then -4. And that lets us kind of keep that x cubed part out of it. Cool.
And when I look at the next one, first thing I notice is it flips over.
Mm,
So there's going to be a negative. My a value is going to be negative. I don't know what my a value is, but it's going to be negative. So let's do the same thing. So we got 0, 0, and that goes to 0, 0. So that didn't move. So that also suggests to me that there's no translation at all. So all I have to worry about, I guess, is the a value. Again, we could think of this as a b value move. We're just kind of refusing to do that.
yeah, it's harder for us to think about things that way.
So I've got 1, 1, and that's to 1/16. So my first thinking is maybe a is -1/16.
Because to get from 1 to -1/16 by multiplying, you have to multiply by -1/16.
And let's check it, see if this one works. So 2/16 goes to 2, -1. Well, 16 times -1/16 is -1.
Hmm.
So I think that's what it is. That's a times -1/16, not an x -1/16. That's a times, just so you guys know. So that's the a value, -1/16 of f of x. And it's interesting that they consider this multiple transformations because it's not, it's one transformation.
Oh, but they're considering the negative a separate transformation from the, yeah.
Or you could also write this as a negative out front and then a b transformation inside, I guess.
Yeah, that would make
Maybe
sense.
that would be two of them. But to me, this is one transformation.
Yeah, and based on the points that they chose to express that, this one doesn't make sense as a horizontal.
Right.
If they chose points that had the same y value, it'd be easier for us to work with.
Right.
All right, here we got a couple more of these things.
So I'm just writing down the points. 2, 0 goes to negative 3, 0. 3, 1 goes to negative 4, 1. And then 4, 64 goes to negative 5, 64. And based on how they marked these points, this is a flip vertically. So that is a B thing that they're trying to get us to realize.
Flip horizontally.
Flip across a vertical line.
Yes.
That's what I meant.
Yeah, I know. Yeah, are you okay with us ignoring that and using the fact that this is an even function?
That's not an even function. It
That
has symmetry.
This is an evenish function?
Well, I mean, sure. Yeah, I mean, we can. It doesn't really matter. However, we want to think about it. The key part here is 64. Oh, there's a 464 also. So those y values don't change. So we don't have to worry about any y changes. So could we just consider this a translation to the left?
Yeah, and that's what I'm thinking about there, that's a lot easier of an ask. So because we can see the symmetry here, and because in this particular section, we're dealing with things that are symmetric in one way or another, I think is a really added important thing. I'm going to argue that there's a point at 2, 1 here. Sorry, at 1, 1 at the opposite side of this axis of symmetry that we have going on here. And similarly on this one, where we got negative 4, 1, we're going to have negative 2, 1 also. That makes it a little bit easier for us to see that you could consider that this is not 3, 1 to negative 4, 1, but rather 3, 1 to negative 2, 1, and 1, 1 to negative 4, 1. And if we do that, then all of these have the same translation, which is moving 5 units to the left. Does that make sense?
Yeah, so it's f. Well, so it's f of x plus 5. We could put a negative in front of that x to flip something, but we're thinking of it as f of x, f of x plus 5. There we go. I said it.
Yeah, and I think that that's a lot easier thing for us to ask our students to do than try to deal with the flipping and then moving stuff.
And then I think for the last ones, I think they can handle this and they should ask about these in class.
I think that sounds good.